Okay, so in this video we have to find out the transition probability when we have a harmonic perturbation. So the perturbation is time dependent now. So the time dependence comes in a harmonic manner. So there is a time independent component, that is V cap. Along with that I have a harmonic term, that is e raised to I omega t. So this is a perturbation, and I'll add another command, b dagger e raised to minus I omega t along with this. So this is going to be the perturbation term that we need to for which we have to find out the transition probability. And it's a straightforward thing. Just substitute this in the equation. PIF is 1 by h cross square, and then you have modulus integral time starting from t0 to t psi f v of t psi I square of it, sorry, e raised to I omega if t1 dt1 whole square. Okay, so v of t here is having two components. One is v raised to I omega t, and another one is v dagger e raised to minus I omega t. So when you take the square of this term, uh, you supposed to have two terms. One is the square of the first term plus another is the square of the second term plus a combined term when you take the square. However, we can neglect the cross term and take the square of the individual terms alone for our consideration. That will be sufficient for our discussion. So the cross term is neglected here, so we will take only the individual terms. Okay, so here when I substitute v of t, uh, my v cap is time independent, so I can just carry away this psi of v cap psi I outside the integral. It's a time integration, so I can just carry that outside this integral and keep it safe and do the remaining part of the integration. And there is nothing but only the exponential operator remains, and the integration is fairly easy. So we just have to substitute the values and get it done. Okay, so first let me take the, okay, there is going to be two terms. So the first term is psi f v psi I square. This is a time independent part of the potential that came outside the integral, and divided by I have h cross square, and later I have this time integration 0 to t. Now here is to I omega t and here is to I omega if t. So this has to combine e raised to I omega if plus omega t1 dt1 square of that. So this is the first term. Along with that we have a similar term, only difference is there in the exponential operator. Of course, this there is a v dagger coming here. Psi f v dagger psi I square of that divided by h cross square, and you have integral 0 to t e raised to minus, sorry, what we have is e raised to I omega if. Okay, e raised to I omega if. You have to subtract omega from that value, so this is minus omega t1 dt1 square of it. So this is the second term, and now we can do the integration. So yeah, once you do the integration, this term will become psi f v psi I square of that h cross square, and here I have, if I integrate this exponential operator, I'll get e raised to I omega if plus omega t minus 1 divided by omega if plus omega square. Okay, yeah, that is the first term. And the second term, okay, we have to take the square of this modulus square, yeah, square of this term plus second term, that is going to be psi f v dagger psi I square divided by h cross square e raised to I omega if minus 1 minus omega t minus 1 okay, square of that, and divided by omega if minus omega whole square. Okay, so this is the second term, and now you have to reformulate this equation. You have to do a little bit of modification for this, and you can make it in the form of sine square function. So this is something that we have done in the case of a constant potential. So I know what is the functional form. I can directly substitute that rather than doing it now. So that is going to be something like e raised to I omega if plus omega t minus 1 square of it can be reformulated into 4 sine square omega if plus omega divided by 2 t. So it can be reformulated into this form, and the other term, which is having a minus, e raised to I omega if minus omega t minus 1 can be written as 4 sine square omega if minus omega by 2 t. Okay, so I want to write the probability in terms of in terms of sine square function, and that will give me PIF equal to psi I v psi f I square divided by h cross square. Okay, when 4 comes here, sine square omega if plus omega by 2 t plus a similar term 4 psi f v dagger psi I square divided by h cross square sine square omega if minus omega divided by 2 t. Okay, so this is our probability expression, transition probability expression. There is two terms, and one is sine square omega if omega by 2 if plus omega by 2, and another one is sine square omega if minus omega by 2. So that is a transition probability equation, and of course it is a sine square function in time, as you can see. And if you plot it in omega, exactly the same way that we obtained in the case of constant perturbation. There is nothing different. Only thing is that there is a change for the omega that we have taken here. Whenever you have the constant perturbation, you didn't have this omega factor. Remaining things are exactly the same. So the functional form is not really going to have any change. Only the point of their omega value is having a slight offset, and that is the only difference in these two terms as also. There is no other difference. You can see there is a variation for this V operator into V dagger, but apart from that there is no other change. Okay, so let us plot one of these. If I plot omega if here and transition probability on y-axis. So where is, okay, I forgot one term here. There is an omega square term in both of these terms. Omega if minus omega square. Here also omega if minus omega, sorry, here plus square. Okay. So due to this factor, okay, as you go further away from this omega if, the value is going to be reducing, and the value will be maximum close to the which value. This is something that we have to see. So this quantity has to be going to 0 for the sine square function to have a maximum value. So the principal maxima for this kind of a function will come whenever your omega if plus omega if plus omega by 2 equal to 0, and this will happen, that is the time the sine square function is going to maxima, not exactly sine square function, sine square by theta square. That function is going to be maxima at this kind of a condition. So omega if in that case will be minus omega. So this is a kind of resonant condition for you. Your omega if, that is the energy between, or the frequency between the two states, has to be what, a minus of whatever your perturbation frequency. If both of them are matching, then you have a higher transition probability. That is, the angular frequency of your perturbation is matching with the what, uh, angular frequency of the difference in energy of the states. That is, this omega if is nothing but this omega if. Okay, h cross omega if is nothing but ef minus ei, or omega if is nothing but this divided by h cross. Okay, so that is nothing but the change in energy of between the states. So whenever you're supplying perturbation is matching with this energy change, then you have the maximum transition probability. So that's what, in this case, this function, as we have seen in the earlier case, it is actually coming to 0. Okay, so this is, in this case, it is minus omega, but in the second case, you have sine square minus omega. Okay, so omega if minus omega by 2 has to be 0, or that will give you omega if equal to omega. So this is a resonant condition for the second term. That is, again, the energy, uh, uh, the angular frequency of between the energy intervals is equal to the angular frequency of the perturbation. Okay, so in this case, in the second case, this is like the transition probability maxima comes at omega. So this is omega if. Okay, so that's our catch from here. Okay, now as before, we have to see what happened uh, if you keep the system for a long time, such that delta t, the variation in time. So you keep the system like this, and uh, yeah, the time is running to infinity. So under delta t tends to infinity, what happened for the system? So you know the proportionalities of omega and probability terms. So this is something that we have seen. Omega, this axis omega if axis, or the width delta variation in omega. So delta omega is going to be proportional to 1 by delta t, whereas PIF is proportional to delta t square, because we have a 1 by omega square on that term. So the entire area is actually not a constant, it's increasing. So area will increase. Area is proportional to delta t. So as the time increases, this area will increase. However, what happened? The width will reduce, whereas the height will be increasing. So this is a kind of change which happened. And at that limit, delta t tends to infinity, it will become a delta function. And of course, we have to do like what we have done in the last example. We have to take the delta function, and that is given by the sine square as sort of an asymptotic function that we have taken, and we can make it into the delta. Uh, yeah, we can find out the expression, but I'm not doing that. I am just taking the expression that we already found out for this constant potential and just adding the correction term. Okay, you can just do it separately. There is no further complications on that. Okay, so this is going to be the equation that we obtained for probability. We actually have written an expression for probability and also for gamma. That is the transition rate. Okay, for in terms of probability, this was like 2 pi t by h cross psi f v. Okay, I have two terms here, so space will not be sufficient. 2 pi t divided by h cross psi f v psi a square of that delta ei. What we have is ef minus ei, and this was the first expression that we obtained. Okay, in this case, I put the direction correction. I will be having an h cross omega along with that. Plus, you have another term 2 by t by h cross psi f v dagger psi I square of it delta EF minus EI plus, sorry, minus H cross omega. Okay, so this is the kind of expression that we are getting for the limit when delta t tends to infinity. Okay, or you can write the gamma expression, the transition rate between initial and final state, as 2 pi by h cross of this quantity. Now t psi f v psi I square delta EF minus EI plus h cross omega plus 2 pi by h cross psi f v dagger psi I square of it delta EF minus EI plus h cross omega. Okay, so this is a transition rate and this is the transition probability, and what it gives you, what is the conclusion from this is that uh, the transition probability, you can take from here, the transition probability is actually 0 for any value at any time. This is not satisfying, right? So there are two instance when the transition probability is non-zero, and one instance is your EF minus EI plus h cross omega equal to 0, or EF minus EI minus h cross omega equal to 0. There are two conditions. At this condition, whenever it satisfies this condition, you have a non-zero value for your transition probability, and all other instances your probability of transition is more or less 0. So this will give you EF equal to EI plus minus h cross omega. Here you have your EF, which is EI plus h cross omega. So what it tells you is that your final energy, or you have actually a transition, your energy is changing here in this case, unlike unlike the previous case, your final energy and initial energy both are not same. So if you're okay, in this case what you can see is that your final energy is actually h cross omega times less than that of your initial energy. So the initial energy is more than your final energy. That's what this case corresponds to. So here this indicates that a photon of energy h cross omega is getting released, uh, and the energy is changing from EI to EF, and this is actually called the stimulated emission. The second case, your initial energy, your final energy is more than that of the initial energy, because you have an additional h cross omega factor here. So initial energy is raised by h cross omega by adding a photon into the energy. So this is actually an absorption process.